Okay, this is 3D software, or as they call 3D software rendering. This is not OpenGL or Direct 3D or anything. This is when you use absolutely no 3D rendering technologies, you do everything yourself. So this is actually a lesson of how 3D libraries like DirectX and OpenGL, how they actually internally work, what they do to basically render the images that they render. How do you take a 3D world and render it on a 2D screen? Because obviously, as you all know, 2D has got 2 dimensions, your X and your Y. 3D has got 3 dimensions, X, Y, and Z. So how do you take those dimensions and just throw away one dimension? Okay. This is also knowledge that I've acquired probably about 10 years ago. So I'm not sure how relevant it is still in today's engines. But I'm sure today's engines works on very similar principles. So if you understand this, you'll be able to just notice the differences obviously in today's 3D engines and how they model these images. First of all, a wireframe. I don't know if you know what a wireframe is. Wireframe is basically, instead of an actual 3D model, you just look at the edges and you connect them with lines. And then you have it's almost like a cube, for instance. This is a typical example of a cube. It's a wireframe. Instead of actually coloring in the cube and making it look like an actual cube, we just connect all the corners and we have a wireframe. That's the first step in 3D, where actually wireframes are used, and then later the textures are applied to make it look like an image. So the first thing it does is obviously it needs to build this wireframe, and a wireframe consists of 2 things, which is points, and then the points are connected with lines. Okay. So I don't know if you guys have used the Cartesian system before. Cartesian system, it's actually supposed to be basic maths, but it doesn't look like it is. If I look at your reactions. Basically there's an x-axis and there's a y-axis. Okay. And on the y-axis there's numbers. There's a number 10, a number 30, and obviously it goes on. So it'll be 10, 20, 30, 40, 50, 60, and it usually goes on till infinity. There's a negative side of the axis as well, so there will be minus 10, minus 20, minus 30, till minus infinity. Okay, can you just watch this thing?
Yeah.
Is it running?
Yes.
And exactly the same with your x. So your x-axis runs like that. And you've got 10, 20, 30, 40, 50, 60, 70 till infinity, and also minus infinity. And then if you have a coordinate on this plane, so in this example I've actually said that the green square could be typically seen as the computer screen. So if you put a pixel, you all know what a pixel is, it's a dot on a computer screen, which is a color obviously, and all these pixels together, millions of them together form an image. If you put a pixel on the screen, it actually has coordinates, which is basically saying how far along the x-axis is this pixel and how far along the y-axis, and that's the location. On this example, I've put 4, 0, 1, 2, 3. As you all know, in programming, we always start counting at 0, not at 1. So yeah, I've actually given these points numbers, and the first point typically would be 10, 10. Usually we write the x-coordinate first, and then the y-coordinate. This is basic Cartesian rules. This comes from maths, not computer programming. Except if you look at the Earth. If you do a geolocation coordinate on the Earth, then you write the y first. Why, I'm not sure, but that's how we do it. So yeah, it's x, then y. So x is 10, y is 10. You can see the lines, that's the point. This one is further along the x, so the x would be 30 and the y would be 10. The second point here, it's 30 along the x and 30 along the y, so it's 30, 30. This one, the x obviously goes back to 10 again, 10 along the x, 30 along the y, so it's 10, 30. That's the third point, or actually the fourth point. So that's how we basically construct points. If you want to put these points in a typical, capture these points and store them somewhere, the good idea would be to put them in an array. So I'll just basically give you an example of how we would store these points. So you'll see here your point number 0, 1, 2, 3 would actually be there. 0, 1, 2, and 3. And here would be your coordinates. So 10, 10 would be 10, 10 here. 30, 10 would be 30, 10 here. 30, 30, and 10, 30 would be here. So here we've basically drawn a cube using points. So if we have a full wireframe of this cube, we might want to say that there's a line between point 0 and point 1. We need to physically draw a line there. It would be a line against point 1 and point 2, so we can draw a line there. Another line between 2 and 3, and we obviously have to know to complete this cube by making another line between point 3 and point 0. Okay, so you have to basically store the point somewhere and store the line somewhere else. The points is obviously just connecting point. The lines is just connecting points. So, let me just think if there was one thing I wanted to. Oh yeah, that's the one thing I wanted to mention. The y-axis. The y-axis in mathematics, it's swapped around. Y, the positive is on top and the negative is at the bottom.
Yeah.
But with computer screens, it's different. On a computer screen, your top leftmost corner is coordinate 0, 0. And as it goes down, y gets bigger. So if you do certain drawings or certain calculations, sometimes what you need to do is you need to actually swap your y around. Okay. But for me, what I used to do, I just used to, instead of using the basic traditional mathematics where y is on top, I would just leave it swapped around. So when I build my 3D world, my y is actually swapped around. Then you basically save one calculation. So your engine would actually render a little bit faster. You'll get higher frames per second by just swapping the whole world around before you even render anything. Okay. So these are just 4 points, and this is still 2D. It's not 3D because it's 2 dimensions, just an x and a y, and we have our points in each dimension. But now we want to make this 3D. So what we can do now is we can add. Basically what happens if you want to make something 3D, you just add an extra dimension, which is usually called Z. And Z, obviously it's going to be difficult to draw it on a flat board because the board's only 2D, but it's basically something that goes into the board. So if I take this pen for instance, and I hold it here like this, that would be the Z axis. And the Z axis goes towards the camera is negative. As it goes into the screen, it's positive. So if something is very far in the distance, the Z value is very big. Yes. Okay. And obviously, when it's exactly at screen level, it's actually 0. So technically, if the Z is negative, it's actually behind the camera. So you won't be able to actually see a negative Z. Okay. So how do we render this now? If we have, let's say we want to take this and convert it to a 3D cube, not just a 2D flat plane. What we can do is we can add exactly the same points. We just add an extra Z. So what I've done, let's take this and just make it a 3D flat plane. So it's not a cube yet, it's just a flat plane. Then we simply add the Z. But now, these are all the same distance from the camera. From the viewpoint, if you want to call it that. And they're 10. Let's say they're 10 points in. It could be 10 pixels, it could be 10 points. Let's just say it's pixels, 10 pixels in. So the Z on all of them would be equal to 10. Because they're all the same. But what you can do now, if you want to make this a full cube, you basically have another plane that's just deeper into the screen. So you have 2 planes. And then the only thing you obviously add extra is the lines that will make it a full wireframe. So you add not just the lines on the other one, now you have to connect the 2 frames with extra lines. So that you'll get something that looks like that. So the first plane would typically be this one here. That would be the first plane. The one that's 10, the Z is 10. The next plane would typically be that one there, which is the Z is 30. But then you need to add additional lines to complete the wireframe. And that's those lines there. So it actually forms a cube. Otherwise, it's not going to be a cube, it's going to be two floating planes that's like close to one another.
Right, as we're looking at it directly from the front, the second plane would have the same x and y coordinates
Yes.
as different z.
I'll get to that now. Okay. So if you, let's say you draw both cubes, and you just ignore the z, there's no z, you just draw them, then they would sit exactly in front of each other. Okay. This is what we call perspective. There would be no perspective. The perspective is just removed. This will look like this. There's actually two planes. It draws the whole block. But because the one plane sits exactly in front of the other plane, it looks like there's only one plane. Okay. If you add perspective, what happens then is you actually add depth. That means you actually use your z value. If something's further away, what happens to it? It gets smaller. Yes. So that's exactly what we want to do. So if we add perspective, the second pane would obviously become smaller than the first pane. So it will look like this. You'll actually be able to see the second pane now. So the bigger one would actually be the front one, which is 10, and the smaller one, which will be the back one, which is 30. Okay. The formula for that is actually very, very easy. I should have written that down. Obviously, your perspective has a certain value, which I don't know what the official term is, but I just call it your zoom value. The bigger it is, the more you zoom in, and the smaller it is, the more you zoom out. But I found that like 256 is like a good zoom value. The cool thing about 256, because you have to divide by it, is that you can use bit shifting to speed up your calculations. Because if you bit shift right 8 times, it's the same as dividing by 256. But it requires one CPU cycle. Okay, so let's just write this formula somewhere. Let's write it, yeah. Okay, so to do perspective, all you say is you say x equals x. I need to think. It is, I think it's times 256 divided by z. Yeah. These are actual times. 256 divided by z. Yeah. Yeah, I think that's right. So, as z obviously gets bigger, it goes into the screen. What will happen? This value here, the total value becomes smaller because it's being 256 is being divided by a bigger number, so it actually goes smaller. Which means your y value gets multiplied by a smaller number, which means your y value will go smaller. So what actually happens is all your points start moving towards the center point. Okay. But this is now another thing that you need to keep in mind. When you draw your 3D world, you actually draw it around center point 0, 0. Whereas with your screen, you only use the positive things. But if you actually, most of your calculations, when you do this depth perception to get to this, your actual Cartesian system doesn't sit like this one there. It actually sits through the middle there and through the middle there. And 0, 0 is in the middle. Okay. So you first need to make sure that that is obviously where you wanted to push the perspective to. If you don't do that, let's say your 0 point is still there, then it will look like this. Where the cube actually, the back of the cube will actually stretch towards 0, 0. Okay. Now, there's a couple of concepts. Obviously, what you can do now is, after you do this perception, you can now just draw the wireframe, because you know where all those coordinates are. You basically take all your coordinates, and you just iterate through them. The first set of coordinates, second one, third, you build a loop that goes through all the coordinates. In this case, we won't have 4, we actually have 8, because we have 2 planes.
Yeah.
This is only the first plane's one. The second plane will obviously be exactly the same x and y's, only the z would be 30. So you'll iterate, you'll loop through all of these coordinates, and you'll push them through these calculations. And then you'll automatically get this perspective. Or if your Cartesian system is still in the original place, you'll get this perspective. where obviously you mustn't look at this side here. It basically goes sideways a bit. And then you have new coordinates. These new coordinates, all you do now is you just draw the lines between them, which is pretty straightforward. Then you have a wireframe that's got perspective. So now you already have a cube that can actually look sort of 3D. It goes sort of into the screen. Is everybody still following? I see you're scratching your eyes and stuff. Are you really following?
Following, just that I don't know what's going in my eye.
Oh, maybe it's the perspective. This is just 2D, it's not real 3D. Okay, so yeah, so that's basically perspective. So but what we can do now, obviously, now you want to start rotating this cube. So just to give you an example of, if you don't use any perspective whatsoever, and no perspective, no rotation, nothing, it'll look like this. If it's just like basically a 2D version. If you start rotating this cube slightly, in like, let's say you rotate a little bit like this and like that, you get something like this, where you're not really sure which is the front and the back side because they're both exactly the same size. Okay. If you only apply perspective but no rotation, it'll look like this. If you rotate it slightly, it'll look like that. Okay. So you see the difference between perspective, rotation, and translation. Wait, we'll get to translation. Perspective and perception and rotation. Okay. Okay. We just quickly cover translation. Translation is very simple. That's just moving all your points. It's a simple plus minus. So let's say you want your Cartesian system looks like this, but you want it to look like that. What do you do?
Zoom out, you move the Z to 0, towards 0.
No, I'm talking about X and Y. Because remember, Z goes into the screen.
Yeah.
So at the moment, yeah, the middle sits outside the cube, because this is the cube.
Yeah.
But now the center point sits there, because that coordinate there is 0, 0. We want 0, 0 to sit here. So what do we do? How do we do that?
X and N one.
Yes, we just subtract all the x's and subtract all the y's. So all you do is you go to every z and you look at, okay, well, if I want to get in the middle, the difference is 15, that's 10, so it's 25. So that means we have to do a minus 25 on all the x values and a minus 25 on all the y values. So we basically go through all of this and we just take this one minus 25, this one minus 25, this one minus 25, minus 25, minus 25, minus 25, obviously. And then it will actually move that point and put it here. Because all these values will change. So actually, that point doesn't move here. Actually what happens is these points move there. Okay. That's also one thing that fools a lot of people with 3D, because in actual fact 3D is not, you don't put the camera in a certain place in the room and rotate a certain way. The camera actually sits fixed. The camera sits and looks down the x-axis and it sits at this position. What we do is we move the whole world.
Yeah.
So you take the whole world, you move it this way, this way, this way, until the camera is in the right position you want it to be. And then instead of rotating the camera, you rotate the whole world to look in the right direction. So everything is a little bit in reverse. Okay, and that's something that catches a lot of people. So basically, at the end of the day, the camera actually stands still. The whole world moves around it. That's what we call translate. So to translate it to where it wants to be. So if you want to be, let's say you build a massive scene, it's not just a cube, it's a massive world you're building. So it's millions of points and millions of lines. And you want to see how it looks like from a specific point. Then you need to add all the x's and y's and z's. You need to add and subtract until the camera is at the right place you want to. So you basically have to move the world into position. That's translating it. Then you need to rotate it. And that's the next thing I'm going to get to, is how to rotate these points. Because that is in essence what makes something full 3D. Just having perspective, that means you can only look one direction, the world can just do this. You can't actually turn and go that way. Okay, so now we're going to cover how to turn something. if you turn something, basically what's happening is that there's three ways to turn something, and we usually refer to the rotation around the axis that it takes place. So because Z goes into the screen like this, if I want to rotate this cube, let's say like that or like that, then we actually call it Z rotation, because it goes around the Z axis. Okay, so this is called Z rotation. Okay, I've written it down here. The irony around it is that your Z coordinates doesn't change. So if you rotate around Z axis, your Z coordinates remains unchanged. The things that do change, your X and your Y. And that's exactly the same with the other rotations. In your X rotation, obviously just like this, that means now that your that around the X axis, so your X sits like this, so now we're rotating like that. Okay, does that make sense?
Yeah.
So that means that your Y and your Z values will change. But your X values actually remains exactly the same. Because how far it sits that way is always going to be the same. It goes up and down, so that's your Y, and it goes in and out, because obviously I go closer and further away. You see, so your Z will change because it goes further and closer, and your Y will change because I go up and down. You see the two things there. So if you look at your rotations, there's actually 3 Cartesian systems you work with, because it's 3D. So basically you separate the Cartesian systems. So if you have an axis here, your one Cartesian system actually sits like this, the first one. The second one sits here like this, which basically uses your Z and your X. The third one uses your Z and your Y, which sits here. So these are your 3 Cartesian systems. And when you rotate, you only apply the changes to one Cartesian system at a time. You don't use more than one Cartesian system to rotate. If you want to rotate like this, and like this, and like this, then you just use 3 separate rotations after one another. But each rotation is still in a single Cartesian system. Okay, so the rotation formula is actually fairly simple. I'm not going to explain to you how it works. I'll give you a hint how it works. If I do this, it'll actually gives the answer away. And that is R and R. That's actually the hint that will actually explain to you how this formula works for this one. But basically, if you have a coordinate there, and you want to rotate at a certain angle. Now these angles are all measured in radians, not degrees. It's always radians. Because all the mathematical operations inside CPUs and inside programming languages does not use degrees. It's always radians. Does anybody know how much radians is in a circle? It's 2 pi r. Yes. Pi is 180 degrees. So obviously 360 degrees is 2 pi. So yeah, if you want to rotate this point around the Z axis, like this now, so you want to rotate it around the Z axis, obviously it's got an X and a Y, and then after the rotation it will have a new X and a Y. And this is the formula. So your new X, let's say this is your old X, your old point, and this is your new point. So your new point's value would be your old X, or your new X would be your old X times the cos value of your angle. Okay, that's obviously the angle you want to, how much you want to rotate it, minus your Y value times your sinus of your angle. So obviously will be that one times the sinus of that angle. The resulting X would be, instead of sitting there, it will just sit there. Now the same with the Y. Obviously the Y's calculation will actually work something like that. But this is the same thing with the Y. You'll see the formula is slightly different. Very important though, a lot of people make this mistake. They take the X there, they don't say X new, they just put the X value there. But you can't do this because this formula, the x you use there, must still be your old x. You can't do this formula and just put this value here in x and use that value here, because then it's going to do weird, awkward stuff. Your world is just going to like do strange and funny things as you rotate it. Okay. So, yeah, always make a new variable so that the old variable is still preserved because you need to use the second formula. When you're done with both these formulas, then you can say x equals x new, y equals y new. Okay. So this is your rotation formula. This is obviously to rotate around the z axis. But now, if you look at these and how the rotation works, it's very simple to get the others. If you want to rotate around the x-axis, all you do is just replace x here with z. Okay, then you rotate around the x-axis. If you want to rotate around the y-axis, all you do here is replace y with z. And you rotate around the y-axis. Pretty straightforward. So yeah, now I can actually rotate. So what do we do now? If we want to rotate this cube, let's say we just want to spin it like that. First of all, your rotation always occurs around your 0 point. So we need to translate it from here to here, so it sits at the center point. Then we can do the rotation. It's around the x-axis, so we actually the z-axis. So we actually use exactly this formula. But we have to iterate through all the points and do it on each point. Okay, so you'll see this is now where a lot of calculation starts coming in. So now this cube can actually spin like that. What you can do now is if you want to physically render it to the screen, you translate it back here to the center of the screen. Oh no, wait, before you translate it back, you need to do the perception. Because remember, the perception always draws the deepest things closer to the center point.
Yeah.
So you first do your perception, so it looks like something like that, obviously. Then you translate it back so it sits in the middle of the screen. So I've just written like a list of to-do things here, how that works. So first of all, the first two, 1 and 2 is to position the camera. Position camera. Okay, that basically translates the whole world. Translate is moving around in the world. Rotation is which direction you're looking. So you first have to do that. Then you create the perception to 2D. We use this formula. This is your perception formula. To basically what that does is that creates 2D from 3D. That makes 2D. So now we're only working with 2D coordinates, not with 3D coordinates. Then we do 2D translation to basically just move this cube into the middle of the screen. And then the final step is just apply the textures. Or if we just do a wireframe, we just do the lines. And that's 3D. That's really the simple part of it. To explain it in the simplest way, I think I can. A lot of people will show you matrices and all these weird formulas, and they have to do maths and stuff, but you don't. You don't need that stuff. If you follow these steps, I mean, this formula you can just type out in code easily. To do cos in Java, you just say math.cos. To do sin, you just say math.sin. And you have these things. So you don't need to know all this mathematics and stuff. It's actually really, really simple. The only thing you're missing is this formula. All the other stuff you've already known. You just need this formula to know how to rotate a point around the center. How you change the x and the y values to actually emulate a rotation. And what we usually do is, once your whole scene has been rotated and rendered, you discard all the values. And you go back to, obviously, let's say you're doing multiple frames. So it's something that flies through a world. So what you'll do is the camera will be at a certain position, you'll render the whole scene, you go through all these steps, you draw it, it's there. But now you want to basically do like a movement, like it's flying through the scene. Now what you're going to have to do is destroy all the points, go back to the regional points. This is very important. Go back to the regional points. Do all the translation and the movement again, but only obviously a slightly different position, slightly different angle. Render the scene. Again, destroy everything, go back to the original coordinates, do your translation, do your rotation just a little bit differently, so it's the next frame, render again. So now you can see how difficult it is to get high frames per second, because there's so many calculations. So next time if you play a 3D game, you can actually look at small like plants and stuff, and you can actually see that it's all flat surfaces. In 3D, nothing is actually round. It's actually just a lot of flat surfaces. And each flat surface has got 4 points around it, which each is a unique point that needs to be rotated and translated and perspective and translated again. Okay, so it's a lot of calculations. And now you want this to happen 100 times per second on a world with 1 million points and textures and everything. So it's quite insane how a 3D game actually runs and what actually happens in the background. And how many calculations there is. That's why you have a graphics card with what they call CUDA cores, where they have like 300 or 400 or 600 or 1,000 CUDA cores, which is CPUs that basically load balance all these. Basically, it's like a 600 CPUs that physically sits in a row, and they just get fed all this data, and the CPUs just need to process everything. Okay, so yeah, but that's obviously not all of it. The last thing I think to explain is texturing, to apply these textures. Okay. Let's see if this thing's still around. Yes. These textures, obviously, once you have your wireframe, if you don't want a wireframe, you can just do, instead of lines, you do textures. A lot of, actually I think all 3D engines, I'm not 100% sure why. I think it's actually just to make sure, that you always have a flat plane. I think that's what it comes down to. But a lot of the 3D engines, all of them, they actually never use 4 points, they always use 3. Okay, and that is a pain. So if you have any surface, I don't know if they call it a clip or a pane, but there's a word for it, which is always 3 points. Okay, so if you actually want to render something like this, you actually have a line that goes through it, and you actually have 2 triangles that you do.
It's actually called triangles or faces.
Faces, yes, faces is the word. I remember. So the reason for that is I think that you can't twist it like this.
Yeah.
It's always, a triangle is always flat. Doesn't matter how you turn it or move the points, it's always going to be flat.
Yeah.
It's never going to have bends in it. So what you can do now is, now we obviously have these points and we need to apply a texture to it. So that's actually fairly simple. If you want a quick 3D engine with no texture perception, which you actually get a thing like texture perception, is you can just, in these squares, you basically take an image and you just squeeze it and manipulate it so it fits exactly in those 4 points. And then it looks like a wall. Okay. The only thing is the texture itself on the wall won't actually have the right perspective. Because if you have a wall, let's say you have a wall that runs into the distance. Oh, no, I run out of space. Let's do it here. A wall that runs into the distance, like that. Okay? So you're basically standing next to the wall, you're looking down the wall. And that's the furthest point, and this is very close to me. If you have no texture perception, the texture will look like that. So those will be your lines. Okay? If you have texture perception, it will actually look like that. You see the difference? So yeah, you can't just take an image and just squeeze it between the points and it will work. Your actual image also needs perspective. So what we do now we go back and use the Z again. So we do still use a wireframe. But along this wireframe, we draw a line in 3D and we add new points. So in essence what we do is we go back to this again. Instead of having just 4 points, now we look at all the pixels in the texture that we want to put on here. Okay, and now we add, let's say the text we want to put on here is an image that's 10 by 10 pixels. So it's obviously very low. But let's make it 100 by 100 pixels. That's the image. It's a very low quality image, but we want to render it on this wall here. So what we actually do, we go back here, and then after all our rotations, so we rotate as soon as we get to, before we get to the perception. So we do the rotate and the translate. Right here, at this point, we can interpolate the new points. So at this point, basically you have something that looks like this. So now what you can do is you create new points from there, yeah, basically from there all the way to there. But obviously perspective hasn't been applied yet. So technically you're still in this unperspective state. Let's say this one. So you're still here. So now you say, cool, okay, there's 100. The image I want to apply is 100 by 100. So then you take that point and that point, you add 100 intermediate points that are all evenly spaced. Obviously just use the simple delta formula where you get the difference between x and the y divided by 100, difference between the x and the x divided by 100, difference between the y and the y, divide that by 100. Then you have the fraction, the distances between these in each dimension x and y. And you just basically start with one and just add these differences. And you basically go along that axis. You have 100 there, 100 there, 100 there, 100 there. Then those are new points. That's now part of this. So you basically take this and you extend it. Then you do your perspective. Okay. Then you know where each pixel should be placed if it does this perspective rendering of the 2D surface. Okay, but that's, like I said, that's very advanced. You can, for now, just do that and just stick with that. But you can just see already that now, just doing all this, how much extra calculations is needed. Now, suddenly, we are adding a lot of extra calculations. We're adding like 100 times more calculations just by adding textures. So it actually looks like something. Okay, but now, the last thing is what they refer to as your Z buffer. Your Z buffer is that so that things don't draw over other things. Because obviously now what you want to do is you actually want to, this cube here, obviously you don't want to see the back piece. Because the back piece is actually not visible. Everything's covering that back piece. So, or maybe there's a cube behind this cube, but you can't actually see that cube. So, there's possibly another way to fix it, and is to draw everything in the right order. So you basically start with your furthest things and you draw them first, and then you draw the front ones last. But there's a couple of problems with that, and that's if two planes intersect, so they physically go through one another, two planes. The other problem is that you always render the whole scene, which is a lot of extra calculation. Obviously, if we put a pixel on the screen that is actually closer to the one in the Z buffer, then we'll update the screen, we'll actually put the pixel on the screen, and we'll update the Z buffer. Okay, but also one important thing to note is this is not actually the screen. This is a virtual screen, it's just a memory location. We've used that to put everything. Once it's done, we've rendered the whole scene, then we take everything there, and then we only draw to the real screen. Okay, otherwise you'll have flickering and all sorts of funny stuff happening. And every time obviously you want to render a new scene, you must clear your Z buffer. The cool thing is you don't actually have to clear your screen, your virtual screen. You don't have to clear it because you're going to draw over everything. And that's also why you'll see sometimes in games when things break, it'll, as you turn, it'll like create this blur.
Yeah.
It's like you actually see the scene, but it's like duplicated. And that's because there's nothing that's rendering over that. And it's a lot of extra time to clear the virtual screen, so they don't do that. It's not needed. If you're seeing that your rendering is completely texturized all around, then you're always going to render the whole screen, except if you're outside it. Then you get that weird, like, yeah, you can see it breaks. It like forms this weird duplication where everything is duplicated. This trail that everything does as you rotate and move around. Okay. There's another couple of things they also do to improve performance. They also look at what, before they even render the face, like in here already, they calculate what objects is behind the camera. Just ignore them. Okay. They calculate what direction the face is pointing. A lot of these faces are only visible from the one side. As soon as you turn it around, they don't render it. Because most objects are covered in faces. So as soon as the face looks the opposite direction, you don't need to render it, because there will be another face closer to it that blocks it. So that way you can save a lot of calculations by doing those removals in the scene already. And that's where most 3D engines actually come in. Like your Frostbite engine and your Unreal Engine and stuff like that. And it's actually all about removing calculations. It's not about making it looking better and stuff. It's more about removing as much calculations as you possibly can.
Yeah.
So looking at this already and seeing what needs to be rendered and what don't I need to render. Because if you go to on the Z buffer as well, I know there was a thing, I don't know if 3D engines use it, but I used it, to see if I want to render something, but all the values are already popular, but I know this face is very far in. So I'll take the closest point on the face, see what area it covers in Z buffer, and see if there's a closer point. If there's no closer point in that area, I just disregard it. I don't render that face. So basically that would be if you're standing right against the wall. So there's a wall right in front of the camera, and there's a massive scene behind it. Technically the only thing you need to render is the wall.
It's the wall.
The scene behind you don't need to render because you can't see it. Okay, so that's where things like that come in. So that's why with certain engines, if you, let's say you see a whole world in front of you, you'll get low frames per second. But as you turn, or let's say you stand in GTA and you see the city, and you'll get, let's say, 50 frames per second. But as you strafe and you walk behind a tree,
You know,
a lot of the calculations will get cut out, so your frame rate will just shoot up because it just ignores all that. And now what engines also do to increase frame rate is they'll actually have different models for different distances.
yeah, billboards.
So what they'll do is you'll have a model of a car, obviously there's a model of a cube, but a model of a car would obviously be very, very complex. A lot of faces, it might be a couple of thousand, 5 faces to model a car. But what they'll do is if this car is a little bit further, they'll have a different model because you can't see it from a distance. If it's further, they'll have a different model. So if you're very far away, you might only have like 8 or 9 faces to render the whole car. They just make everything flat. But because you're far away, you can't really see the details. You see?
Some of them have
So-
short distance as well.
Yeah, like
Yeah, sometimes if the car is smaller than a certain size, they even skip the car in total. That's sometimes called referred to as the draw distance.
What they do with a lot of the props, like trees and buildings, is at a certain draw distance, they change them into billboards where it's a flat
Yes.
pane. That's
Yeah,
just
it's
a
actually
texture.
just one pane.
Yeah, that's a
So they basically
texture
convert it to one
that's
pane.
stuck
But
on.
that's something obviously that doesn't really move and have an angle and stuff. Like a car would be difficult because a car like drives up and down stuff, but a tree is fine because it's
Yeah.
always standing upwards. So as you turn, it's actually a face pointing towards you.
It's actually still,
And as you move closer, it'll suddenly snap and it's an actual 3D object.
it's actually still
So-
6, I think it's 6 panes that they use in a cross shape, so that if you strafe, it still creates the effect of the entire tree being there. But it's just different panes with the same texture at different angles.
Yeah. But even grass, for instance, if you look at grass, in
Yeah.
most 3D games you look at the grass, sometimes the grass is actually just one long texture. It runs
Yeah.
like this. And another long texture runs like that. So I actually have all these textures like this and like that. But obviously the textures are transparent. So it looks like grass. But if you look close, you'll see actually glass is completely flat. It's just a texture that's just like that. But then you also get a fully 3D rendered grass,
Yep.
which they physically have a model for each grass stem. But that's a whole other.
Unreal Engine.
Yeah, that's like, yeah. But technically you can do that if you take distance into consideration. If you're close, you model the full grass stem, but if you're far away, you snap in the image. And if you're very far away, you might even remove the grass completely and just have the ground there. Because you can't see it. That's why in Battlefield, for instance, if you're very far away and you snipe, you can actually see all those defects. The textures actually, they drop the texture quality, the models become different. Sometimes you see a guy and then you shoot him, but you can't hit him.
Yeah.
It's actually because there's another model in the way. But because of the
You don't
engine,
see
it doesn't render the thing that's in the way. It's actually starting behind the rock. But the engine doesn't render far things that are very far, so it doesn't render the rock. So you just can't cheat him. There was one other thing. Oh yeah, the Z buffer as well. That's also a thing that you'll see in especially Battlefield. Seen that? Your Z buffer uses floats for these values, for distances. But how a float works is that, the float stands for floating point. So your precision gets lost as the value increases. So if you have a float that's very big, you actually lose the ability of fractions. You don't have fractions anymore if the value is very big. The bigger the value gets, the less accurate it gets. So what happens in Battlefield, for instance, is you have two walls, or you have an alley. If this wall's very, very far, it sometimes renders the back face over the front face. So you start seeing through buildings and stuff. So sometimes somebody would be in a hallway, and you can see the guy. Because it's so far, and you zoom in with the scope, you can actually see the guy. But actually he's behind the wall.
Yeah.
But because of floating point correction being lost at big ranges, you can still see the guy. Or you can see parts of him or something. So yeah, sometimes you have a gun that can shoot through a wall. That can be very, very convenient. Very convenient, but okay. Does that actually answer some of the questions?
Yes.
Yeah.
I just have a question.
Yes.
On those arrays, is it pure arrays or do we use points or vectors in Java specifically?
Okay, in Java, well, obviously you can decide, that's where it comes up to you, your 3D engine. What are you going to do? Most 3D engines, obviously is broken down into models.
Yeah.
So you won't have one array that's the whole scene.
Yes.
You'll have models. And a model will have a list of points.
Points, yeah.
I would suggest using arrays, using this method.
Okay.
The pure reason is that array is very fast.
Yeah.
It's very fast to access index an array because of how the memory allocation internally actually works, especially if the array is predefined.
Yes.
But something like an array list will not be as fast because an array list, as you populate it, it will actually allocate different memories in different locations. So if you actually access element number 100, it might actually do a couple of jumps internally in order to fetch that value.
Okay.
Whereas if you have a predetermined array length in Java, it will actually store everything in the memory from here to there, will be dedicated to that whole array. And if you access index number 100, it will just jump to index number 100 and return the value, or set the value. So you will get a big performance increase if you use arrays. But the ideal would be to use obviously arrays, but you'll have an object with arrays inside of the coordinates, another object with arrays inside the coordinates, all the textures, etc., etc. It's all broken down into objects. So an object would be the ground or a section of the map. Another object would be a building, another object would be a tree, another object would be a car. So because then also it gets easier at long distance to stop running certain type of objects. So then your frames per second increases significantly. Okay. Oh yeah, one last thing is the order of rotation. Obviously, if you do 3D rotates, like I said, there's actually 3 rotations you need to do.
X, Y, and Z.
If you build a simple first-person shooter game, the most important thing is that your order of calculations. Otherwise, you're going to struggle with this. Is the first thing you need to rotate on is actually your y-axis. Okay. You always rotate y first. So that means the character as it's turning, always rotate that first. Then you rotate your x-axis, which is up and down. Okay. And you never actually rotate y-axis. Unless you want to emulate the guy falling down or something.
Yeah.
But just the guy running around and shooting, you actually never rotate z. You only rotate x and y. So y first, so you turn and face the right angle, and then x to look upward that way.
Yeah.
Otherwise, it gets very weird, because if you do x-axis first, you might look up like that, and then you rotate, and it will rotate like that,
Yeah.
and then you look down suddenly. So it can go very weird. It can be real weird results, and it doesn't make sense. But it's just the order of rotations that you need to look at.
But in a motorbike game, you can do the z-axis though. 'Cause you're
Yes, yeah, because you're leaning and stuff like that. But then it's very important that the z last.
Okay.
So it's actually y, x, and then z.
Okay.
Okay, cool. Is that it? We've got a bit of an idea of how it works. Yeah, well, I've got that JavaScript file that I've written. I'll also actually put it on the video with that rotation cube. It's like 100 lines of code. It basically does all of this. It just doesn't do the textures in the Z buffer there. But it basically has a cube, and the faces are actually solids, and the cube spins, and I think there is access perspective as far as I remember. Okay, cool.
Cool.
You guys happy? Makes sense. Awesome.